Welcome to this explainer. Today, we're going to unlock one of the absolute most fascinating mysteries of the natural world. It's a continuous, invisible to visible cycle that's happening right above our heads, and it literally dictates the weather we experience every single day. We are talking about water in the atmosphere. It's this non-stop exchange between the sky, the oceans, and the continents. And let me tell you, understanding how it works will completely change how you look at a cloudy sky or a rainy afternoon. Okay, let's dive into this. Here is our roadmap to make sense of these complex mechanics. We'll be looking at invisible water in air, the magic of condensation, decoding the clouds above, when the sky falls, 3 ways to make rain, and finally, global rainfall patterns. Starting right off with Section 1, invisible water in air, or the hidden ocean all around us. Now, you might not realize it, but thanks to evaporation from the oceans and transpiration from plants, we are essentially walking through a hidden gaseous ocean right this second. Seriously, take a deep breath, look at the seemingly empty air in the room with you. Unless you happen to be watching this in a sauna, it probably feels pretty dry, right? So, how much of the air around us by volume is actually made of water? The answer? It varies from exactly 0 to just 4%. That's it, a maximum of 4%. Yet this tiny, seemingly insignificant fraction of water vapor is the mighty engine driving absolutely every weather event on our entire planet. When we talk about this invisible water vapor, we usually just throw around the word humidity, but there are actually 2 totally different ways to measure it. Absolute humidity is the actual physical amount of water vapor present in the atmosphere. We're talking the literal weight of the water per unit volume of air, usually measured in grams per cubic meter. Relative humidity, on the other hand, is a percentage. It measures the moisture present in the air compared to the absolute maximum capacity that air could hold at a specific temperature. You see, warmer air can hold way more moisture, so as the temperature changes, the relative humidity changes too, even if the actual physical amount of water in the air stays exactly the same. Moving on to Section 2, the magic of condensation, going from invisible to visible. This is the incredible story of how water transforms from a hidden gas back into something we can actually see. It's a step-by-step process. Step 1, moist air cools down, which usually happens when it rises. Step 2, it hits what we call the dew point. That's the specific temperature where the air becomes completely saturated. Step 3, because it's cooled off, its capacity to hold water ceases. It literally cannot hold another drop. And step 4, all that excess water vapor has to go somewhere, right? So it condenses into a liquid. But here's the catch. It needs something to grab onto. In the open air, it condenses around microscopic particles called hygroscopic condensation nuclei. Things like everyday dust, smoke, and even salt from the ocean act as perfect little catchers because they naturally absorb water. Sometimes, this condensation happens right down at ground level. If the dew point is above freezing, the excess moisture just deposits as water droplets on cooler surfaces, like stones or grass. We call that dew. But if the dew point is at or below the freezing point, we get frost. Instead of turning into water droplets, the excess moisture completely skips the liquid phase and deposits directly as minute ice crystals. Pretty cool, right? Let's look up for Section 3. Decoding the clouds above, or the sky's canvas. What happens when this condensation occurs way high up in the free air? Well, the sky essentially becomes a canvas, and it's like a giant puzzle. We classify these floating masses of water droplets and ice crystals by their height and what they look like, mostly using Latin names. First up, cirrus clouds. These form 8 to 12 kilometers up. They're detached and feathery white. Lower down, between 4 and 7 kilometers, we find cumulus clouds, which look like scattered patches of cotton wool. Then you have stratus clouds, which absolutely live up to their name by forming vast covering layers. And finally, nimbus clouds. These are your dense, dark gray clouds hanging low to the ground. And this brilliantly illustrates the concept of scattered cumulus clouds in reality. They really do look like floating tufts of cotton, don't they? But pay close attention to their flat bases. That flat bottom isn't some random coincidence. It marks the exact, specific altitude where the rising air cooled down to its dew point and condensation began. On the flip side, contrast that with the darker, incredibly dense nimbus or thick stratus clouds. These shapeless masses are so thick they actively block out the sun's rays. And when clouds start looking heavy enough that you could practically touch them, well, that almost always signals our next topic. Which brings us to Section 4, when the sky falls and gravity takes over. Through continuous condensation, those tiny cloud droplets keep growing and growing until air resistance simply fails to hold them up against gravity. And that is precipitation. Moisture is released in a few forms: liquid rain, or if the temperature is below freezing, hexagonal snowflakes. But then we have two sporadic forms: sleet and hail. Hailstones are actually fascinatingly violent. They form when rainwater gets constantly tossed up and down through colder layers of air, freezing into solid ice. If you were to cut a hailstone open, it literally looks like an icy onion with concentric layers. Then we have sleet. So the crucial point here is how highly specific its formation is. Most people think sleet is just really cold rain, but it's not. It's frozen raindrops and refrozen melted snow water. It happens uniquely when a layer of warm air, above freezing, sits perfectly over a sub-freezing layer of air near the ground. The raindrops leave the warm air, hit the cold air below, solidify, and smack the ground as small pellets of ice. Next up is Section 5, 3 Ways to Make Rain, examining the mechanics of uplift. So, we know what falls from the sky, but why exactly does the air rise and cool to make rain in the first place? Well, it happens in 3 distinct ways. Convectional rain happens when heat from the ground causes air to rise, expand, and cool. That's what often gives us those short, heavy summer thunder showers. Then there's orographic, or relief rain. This is when moving air is physically forced up and over a mountain slope. Finally, cyclonic or frontal rain happens through the complex clashes of different air masses in extratropical cyclones. Let's look a little closer at orographic rain because it creates a truly wild geographic phenomenon called a rain shadow area. When air is forced up the windward slope of a mountain, it cools down and dumps its rain. But by the time those winds cross the peak and reach the leeward slope, the backside of the mountain, they start to descend. And as they descend, their temperature rises, which actually increases their capacity to hold moisture. So instead of dropping rain, they hoard it, leaving the leeward side practically a desert. Finally, Section 6, Global Rainfall Patterns. Let's see who gets the wettest. Zooming all the way out to a planetary macro level, the processes we just discussed distribute water very specifically across the globe. The general rule of thumb is that rainfall decreases as we move from the equator toward the poles and from the coasts toward continental interiors. The equatorial belt and coastal monsoon lands are absolutely soaked, receiving over 200 centimeters a year. Move inland, and that drops to a moderate 100 to 200 centimeters. Central tropical and temperate lands see about 50 to 100 centimeters. And finally, areas in deep rain shadows or near the frigid poles are essentially atmospheric deserts, getting less than 50 centimeters annually. We've traveled all the way from the invisible gas in the very room with you to the formation of clouds, right down to the mechanics of rain and its distribution across the entire globe. So I want to leave you with this question. Based on the global patterns we just explored, thinking about your latitude, your proximity to the coast, and your local mountains, which rainfall zone are you living in right now? I highly encourage you to look up your local atmospheric data and see if the sky above your house matches the science. Thank you so much for joining me on this explainer, and definitely keep your eyes on the clouds.